on topological semimetals. So I'll start with the canonical example of Vial Fermions, and then move on to Dirac Fermions. And there's been some interesting work that I've been involved in trying to figure out the analogy of the bulk edge correspondence for Dirac Fermions. And then I will talk about generalizations of that, which is the multifold fermions. And there's been some experimental updates on that since we first predicted those now several years ago. So to start out, let me just make some overarching comment, which is, when I first heard of topological semimetals, the concept was very confusing to me because everything we've talked about in topology so far has been about insulators, and it's been very important to keep the band gap open. So I didn't really understand what was protecting these phases. I thought it must be fine-tuned in some way or not very robust. But the thing that happens is that if you have a semimetal, and if the Fermi level is not exactly at that band crossing point, then you have a Fermi surface, and the Fermi surface is only crossing the gapped areas of the band structure. And so you can define topological invariance on the Fermi surface. And so that's how we can rigorously define topological invariance of semimetals on their gapped Fermi surface, which is in one lower dimension. So that's the overarching picture of how semimetals can be topological. And now I'll start from the beginning. So Biofermions, probably most people have seen or heard something or a lot about this. So Biofermions are linear crossings between two bands. So whenever I have a band crossing just between two bands, I could expand the Hamiltonian in the basis just of these two bands. So we can use Pauli matrices to define that basis. So I'll always have a 2x2 Hamiltonian, which I could expand in increasing orders of K. And if that expansion is linear, then I can always do some basis transformation and rescaling so that the Hamiltonian is just K dot sigma. And this is the canonical Hamiltonian for a Vial Fermion. We could give a whole week's worth of lectures on Vial Fermions. So this is a very symmetric form. Importantly, there's also been type 2 Vial Fermions, which have a tilt factor. We could also consider anisotropy. So there's a lot of different topological deformations that we can make to this. But for now, let's just think of this simple form, and any smooth deformations of this won't really affect the topology. So some important points about Vial Fermions. They don't require any symmetry to protect this crossing. That was another thing that threw me off when I first started learning about this. How can there be a band crossing that doesn't have any symmetry protection? How can we not gap it? I think the easiest way to understand this is that suppose you have this K dot sigma Hamiltonian, and suppose you were to try to gap it by adding in some other term, any one of the Pauli matrices. You can see that since all the Pauli matrices are present already, any additional term that you add will just move the Vial Fermion around. So it'll open a gap at one place, but it'll be closed somewhere else. And this has been, this cute phrase, movable but unremovable, has been used to describe this situation. We can move these things around, but we can't get rid of them. A different way to understand why Vial Fermions don't require any symmetry protection is that in a three-dimensional system, we have our Hamiltonian in momentum space as a function of three momenta, kx, ky, kz. And since we're expanding in a basis of Pauli matrices, we have three Pauli matrices, sigma x, sigma y, sigma z. And so in order to get a band crossing, if we expand the Hamiltonian in the basis of Pauli matrices, we'll get three functions, which are the coefficients of sigma x, sigma y, sigma z. So we have three functions of three variables. And a band crossing occurs when those functions all have simultaneous zeros. And so three functions of three variables can have zeros without any fine tuning. And so that's why this doesn't require any symmetry. And if we were in a different dimension or had different numbers of bands crossing, the situation would be different. Okay, so now moving on to the topology of these things. The point here, as I was saying earlier, is that we can look at the Fermi surface. So a Fermi surface will be a sphere. And that sphere is now a 2D manifold. And as long as the Fermi level is not at zero, it's a 2D manifold where there's a gap everywhere on the Fermi surface. And so we can compute the Chern number on the Fermi surface. And it turns out that that Chern number is always plus or minus 1. And so that's what gives us the topology of these Vial fermions. And so I just wrote out this calculation here, not expecting you to do it right now, but just to show that there's nothing tricky about this. It's pretty straightforward. Last time we wrote down this formula for the Chern number, but now instead of integrating over the 2D Brillouin zone, we're going to integrate over the Fermi surface. And so all you need to do is compute the Berry connection. So if you take the block wave function of, say, the valence band, you can compute this Berry connection. It's easiest to do in spherical coordinates. And then you can see that the Chern number will either be +1 or -1, depending on if you take the conduction or valence band. And so we say that a Vial fermion is a source or a sink of Berry curvature. What this means is that the Berry curvature in this spherically symmetric case, the Berry curvature is always pointing outwards all over this sphere. And so if you wanted to, there's a consequence of this. So that's why it means it's a source, because the Berry curvature is always pointing outwards and it's originating from somewhere in the middle. But now if we try to shrink this sphere, so this is the sphere that I'm thinking of, and if I try to shrink it together, somewhere something pathological has to happen, because this Berry curvature is everywhere pointing outwards. But which way should it point when we get to the origin? And the only way to resolve this pathology is to have a gapless point in the middle. So if you have any source or sink of Berry curvature, there has to be a gapless point in the middle. And that's exactly what the Vial fermion is. And this, the topology of Vial fermions is related to these first 2 points. The reason that we can't remove a Vial fermion is exactly because it is topological. So we can understand it in terms of Pauli matrices, but we can also understand if we have some source of Berry curvature, it can't just disappear. And so this is the, I think this is the topology of Vial fermions. Consequence of this topology is that there's going to be edge states, which in this case take the form of surface Fermi arcs. So remember, last time we talked about if you have an insulator with a Chern number, then there's always going to be one gapless edge state, which is connecting the valence band to the conduction band. Now let's move to our Vial fermion system. So this is some cube of material, which is meant to be infinite in the X and Y direction. So that's momentum space, but finite in this in the Z direction. So it's a slab configuration. And I just said that the Fermi surface surrounding one of these Vial points has to have a Chern number. And so if you think about taking your Fermi surface and deforming it, you can deform it into 2 planes. And since the Fermi surface had a Chern number, it must be that the Chern number on these 2 planes differs by 1. So one of these planes also has to have a Chern number. And since we just recalled that planes with a Chern number have gapless surface state, then this plane has to have a gapless surface state. And so each one of the planes in between these 2 Vial fermions will contribute 1 gapless surface state. And so there'll be this chain of gapless points which are connecting the 2 Vial fermions. And that's exactly what the Fermi arc is, because it gives you a surface Fermi surface, but that surface Fermi surface ends at the 2 Vial points and makes this little arc across the surface. And these, so this is just to show some data. In this previous slide, it seems so clear. It seems like it would be very easy to observe this. Actually, the data is a lot more complicated. One of the problems is that a lot of Vial materials have many Vial points. So one example of this is Tantalum Arsenide. This material has 24 Vial points. Some of them are drawn here by these black and white dots. So when you look at the surface, you actually get projections of many Vial points. So this is a depiction of the surface in momentum space. And so color here is representing a plus or minus Vial fermion, and these numbers 1 or 2 are telling actually when you look down on the top surface in this material, there's multiple vials that project to the same point. They're related by symmetry. So they literally project to the exact same point. So a charge of 2 is saying there's 2 vial fermions here and their combined charges too. So we have all of these vial points, and this picture is not drawn to scale. Actually, they're a lot closer together. So on this right-hand side, this is a theory calculation of what the surface would look like. These black and white dots are still here. And you can see that these Fermi arcs are actually these little tiny arcs, which are connecting 2 vial points. And there's 2 of them because these 2 vial points have a charge of 2. That's the theory calculation. So still, the data is even a little bit less clear. And so this is what the data looks like. You can see it matches pretty well to the theory, but these are actually the Fermi arcs. Questions?
Yeah, there are 2 questions. So the Fermi arc is obtained because for each K point between the vial point and the Vial, you can define this construction with planes with a Chern number.
Mm-hmm. Yes.
Yes is the response. Okay.
Yes. Yep. That's exactly right. So just to say, yep, these planes have a Chern number. Planes that have a Chern number have gapless edge state, and every gapless edge state will cross the Fermi level in some place. And so if we fix the Fermi level, there'll be a state there, and then that's the Fermi arc. It's the collection of these states.
The second question is there a way to predict the trajectory of a Fermi arc?
Oh, that's a great question. So first, let me say there could be some confusion, which is you don't know, like in this picture, it has Chern number of 0 plane, Chern number of 1 plane, but maybe you didn't know which was 1 and which was 0. But that is not ambiguous because we can always compute the Chern number of any plane. So we always could know whether the Fermi arc should be going this way or say outside of the Brillouin zone. However, the path that the Fermi arc takes is really determined by microscopic details on the surface. So I don't think that there's a way you can constrain these details by computing, just by computing topological invariants, and maybe you could compute in different planes and get further constraints. But this line could be curved, could be straight, could be moving all over the place. And, you know, as you see here, there's some curvature to these, you know, but it could be a lot bigger of a curvature. So those details are determined by the surface details, which might even be different from material to material. Interestingly, it can also be different if you truncate on different planes. So say you have some crystal which has different types of planes, maybe because there's different types of atoms. And if you truncate on the A atoms versus the B atoms, that could change the shape of the Fermi arcs. So you can make some progress with ab initio calculations, but still there may be surface details like reconstruction that's not accounted for in there. And so I think it's very hard to precisely predict the trajectory of the Fermi arcs, if that's a good question. And I'll later show some examples which are even crazier.
So actually there is another question following up the last one. If you don't know where the surface states appear on a sample, are they useful for any potential application?
What I'm saying is that they're difficult to predict their exact shape, but they're highly constrained in the fact that they'll always need to say start at a plus and go to a minus. So I think you still have enough information to maybe use this for some application, but also it may be that every time you cleave a sample the same way, you will more or less get the same Fermi arc. So I'd expect that there's some consistency, but I don't think you can, from theory, 100% predict the trajectory of Fermi arcs. And at this point, you know, applications is a great question. And I'm not sure that if there was any application for Vial Fermions, I'm not sure that it would rely on the Fermi arcs or maybe some other properties of vials, like their transport properties.
Mm-hmm.
Yeah.
Okay, thank you.
Yeah, thanks. These are great questions. So the other thing that I want to say about biofermions is this chiral anomaly. So this is actually, I'm going to show some data on sodium bismuth. Sodium bismuth is actually a Dirac material, but in a magnetic field with a Zeeman term, the Dirac point, which I'll talk about in a bit, splits into two vials. So for now, let's just treat this as a vial material. The important thing here is that I want to talk about Lando levels for vial fermions. So last time we talked about Lando levels in 2D. The difference for Lando levels in 3D is that they can have a dispersion parallel to the magnetic field because there's one extra dimension in there. And so as in graphene, for any Dirac cone, when you compute the Lando levels, you'll get a 0th Lando level. So that's what we're seeing here. Just look at one K point, you get all these Lando levels, you get a 0th Lando level, and then you get some others. And the spacing is different than for the free electron gas. But it's the same thing as for graphene. And I'll refer you to this review article for more details on this. But now this 0th Lando level has to disperse. And so it has to choose to either be, left moving or right moving. And the way that it chooses that is based on the chirality of your vial fermion. Vial fermions always have to come in pairs. I didn't say that before, but maybe it was obvious. Maybe it wasn't. If you have a source of barrier curvature, you also need to have a sink somewhere else. And so by the periodicity of the Brillouin zone, the vial fermions always come in pairs. And so you'll end up with a set of Lando levels for one vial fermion, which has a chiral mode in one direction. And then for the other vial fermion, it'll have this chiral Lando level in the other direction. And okay, so that's the Lando level structure. Now, if we apply an electric field, what happens is that an electric field will change the occupation of these chiral Lando levels because they cross zero energy. And so these levels must connect somewhere deep down below the Fermi level. And if we apply an electric field parallel to the magnetic field, electrons will be pumped from the left moving type to the right moving type. And so there's a charge pumping between the left and right vial fermions, and you can compute the rate of this, and it goes like E dot B. And so one way to test this in an experiment is to compute magnetotransport in a magnetic field and change the angle between the electric field and the magnetic field. So that's what this little schematic is showing us. They're measuring current in one direction. That's the direction of the applied field. And then applying a magnetic field, which is separated by some angle, and they're varying the angle between these. And all these different lines are showing all these different angles. And so when E is parallel to B, that's like these 0 degree plots. Then what happens to the magnetoresistance is that as you increase the magnetic field, the resistance decreases, which means conductance is increasing. And so that conduction is exactly the conduction that's resulting from this E dot B term. And this is called the chiral anomaly because what it means is that left and right fermions are not conserved. That's basically the definition of chiral anomaly. It's anomalous in high energy physics. In condensed matter physics, it's not really anomalous because we know that these bands must connect somewhere. Band structures are always continuous. And so it makes sense that you can pump from one to the other. But if you just look at the low energy theory, the left and right fermions are disconnected from each other. And so it's a little bit strange that you get this pumping. So that pumping results in a current. The current goes like E dot B. And so if we increase the magnetic field, we get an increased current and decreased resistivity. And that's the negative magnetoresistance that we see in these 0 degree plots. If we go to 90 degrees, you can see that the shape of these curves completely changes. E dot B is 0 at exactly 90 degrees. And there we get more normal magnetoresistance, which is as you turn up the B field, the resistance increases, electrons become more localized. So the point of me showing you this is it's just to show that when people talk about negative magnetoresistance, that's a defining feature of vial fermions, and these are the types of plots that it's referring to. So just to summarize, why would we care about vial fermions? I've shown you some interesting experimental observations, and one that I didn't talk about, which is quantum oscillations between the Fermi surface is not just in the bulk, but also connects to these surface Fermi arcs. And so you can get surprising types of quantum oscillations. So on the experimental side, there's some interesting phenomena that you don't see in other systems. On the theory side, I think it's really interesting because we have a lot of concepts that are coming together. So in particular, the roles of symmetry and topology are all interplaying in these Vial systems. Obviously, the topology is quite evident through the Chern number. And then there's also this interplay between with high energy physics, which has actually gotten some people who worked on the chiral anomaly in different contexts in high energy physics interested in condensed matter physics. So from the theoretical side, it's also a pretty fascinating topic. But I think that the real reason why this field of biofermions took off about 6 years ago is really because of this interplay between the two. So the ability to do ab initio calculations, which are very accurate, predict materials. You can directly compare the data. You know, ARPA's data is something that you can directly compare to ab initio calculations quite easily. I think this interplay between theory and experiment is what is really interesting about this field and what was driving it forwards. And so I think that's why this became so popular. So now I want to move on to Dirac Fermions. So Dirac Fermions are in some sense two copies of Biofermions. They occur when two bands, so doubly degenerate bands, cross another group of doubly degenerate bands. And so I want to say a little bit first about the role of symmetry. So inversion symmetry and time reversal symmetry are the most crucial thing here. They both map K to minus K. So inversion symmetry flips the chirality of a Biofermion. This is because if we think back to that K dot sigma Hamiltonian, inversion symmetry takes K to minus K. And so Biofermions of K dot sigma and minus K dot sigma have opposite chirality. Time reversal symmetry also takes K to minus K, but because it's anti-unitary, it also flips the sigma Y matrix. And so if you think every time you flip one of the K directions to minus itself, you flip chirality, time reversal effectively only has two flips. And so it leaves chirality invariant. Therefore, the product of inversion and time reversal leaves every K point invariant, but flips chirality. And so this would forbid the existence of a Biofermion because it says that every time you had a Biofermion, the combination of P and T would give you back another Biofermion at the same point with opposite chirality. So Biofermions are not allowed if you have both inversion and time reversal. But if you do have both of those things, that can protect a Dirac fermion. And so one way to think of a Dirac fermion is as a combination of a plus and minus vial with opposite chirality on top of each other in momentum space. Now, it requires not just this PT combination, but also rotation symmetry to protect this. And so I think it's actually, to me, the easiest way to think of this is, let's do an example, which is suppose that we have fourfold rotation symmetry along along the Z-axis. Then along that axis, bands have fourfold rotation eigenvalues. There's four possible eigenvalues, which are the fourth roots of -1. And so two bands, the PT, inversion times time reversal symmetry, will cause bands to be doubly degenerate. And it will, because of the anti-unitarity of time reversal, these doubly degenerate pairs will have opposite fourfold rotation eigenvalues. So, but since there's four possible eigenvalues, if you have one pair with, say, eigenvalues e to the plus or minus I pi over 4, they can cross another pair with the other two eigenvalues, e to the plus or minus 3 pi I over 4. And this crossing will be protected by rotation symmetry, but also this combination of inversion and time reversal symmetry. And so inversion, time reversal, and rotation can protect Dirac fermions. And what the other thing to say here is that the rotation has to be either 3, 4, or 6-fold. If you only have a 2-fold rotation, then you only have 2 eigenvalues. And so there's not pairs of eigenvalues that can cross in this way. So the next question is, are Dirac fermions topological? So originally, at least when I started working in this field, I heard from conversations that Dirac fermions would have Fermi arcs. And so I think this idea was floating in the literature. And the thought was, if we can think of a Dirac fermion as 2 vials on top of each other with opposite charge, and there's some other Dirac fermion somewhere else, also 2 vials on top of each other, each of those vials should contribute Fermi arcs. And so you should have double Fermi arcs like this. This really neat paper, there's actually 2 papers by this group, showed that this was not true. In fact, if you write down the simplest model of a Dirac fermion, some 4-band model, then yes, you will get these double Fermi arcs, but they're not symmetry required. And as you add more terms, generic terms to your model, these things can detach. They can form some detached Fermi surface, and then they can go through other types of topological transitions. And there's some instances where they can be completely removed. So Dirac fermions are not required to have gapless surface states. Question?
Yeah, there is a question by Maxime Gorlach. I wonder if Dirac point can arise in the gamma point in the system with C4 symmetry. Isn't it a quadratic band crossing instead?
Yeah, so this is somewhat of a question of semantics. So I'm talking about this type of Dirac point on a high symmetry line. Yes, you can also have fourfold band crossings protected at the gamma point. Those are a little bit different. You know, they don't occur from this mechanism. So when I'm saying Dirac fermion, I'm actually only going to be talking about these for today. But yes, you can have symmetries in the cubic space groups. You end up with quadratically dispersing bands from gamma, and that's also a 4-band crossing. But that has, it's a little bit different. It's a little bit different than this, and I would expect it to have different properties. So I'm going to kind of keep that separate.
Mm-hmm.
Okay, great, good question. Okay, so Dirac fermions don't have a bulk edge correspondence, and so you might deduce from that Dirac fermions don't have any topological properties. So now I'll try to convince you otherwise. So the first argument that Dirac fermions could be topological is what I said before. Dirac fermions secretly have 2 Vial fermions inside of them. And so if you apply a field, you'll split your Dirac point into 2 Vial points. And so this is the example of sodium bismuth that I showed before. And in addition, actually, this is directly related to the previous question. One thing that we studied several years ago was, suppose you have one of these quadratic band touchings at gamma and you apply a magnetic field, then this also will give you Vial points. So somehow Dirac fermions are some kind of parent phase for Vial fermions. So it seems like they have some hidden topological nature inside of them. But even more compelling than that is this idea of a higher order Fermi arc. And so this will give us some kind of bulk edge correspondence. It will actually be a bulk hinge correspondence. So to understand these higher order Fermi arcs, we need to return to the idea of the quantized quadrupole insulator or higher order TI in 2D. So I'll first talk a little bit about this model, and then on the next slide show how this gives us these higher order Fermi arcs. So what is this model? It's saying that in 2D, if we have the appropriate set of symmetries, including this 4-fold rotation, then you can get a quantized dipole moment, which is vanishing, and a quantized quadrupole moment. And so this quadrupole moment, which is quantized, will tell us that we need to have corner states in our system. So vanishing dipole means that we have gapped surfaces, but there'll be charges on the corners where 2 surfaces meet. And so in this paper, they provide some explicit model of this. There's 4 sites in the unit cell, and there's 2 different types of hopping terms. And so, so this gives us a 1-parameter Hamiltonian, so we can plot the energy spectrum of our 2D system as a function of the ratio of these parameters. And we see that there's 2 types of insulating phases. Here we'll just get some kind of band gap. This will be a normal insulator. But once we cross some critical point, then we start seeing these mid-gap states. And if you look at the spatial localization of these states, you see that they're localized at the corners. And so this, and so that's what the higher order TI or quantized quadrupole insulator phase is. It's an insulator, and it has mid-gap states, which are localized at the corners of the system where 2 surfaces meet. And this invariant is protected by these symmetries that I listed here. There's different combinations of symmetries that you can consider, but in this case, they're considering mirror symmetries, inversion symmetry, and a 4-fold rotation symmetry. Okay, so now coming back to our Dirac material. So this is some schematic. These are my 2 Dirac points. I actually have all those symmetries that I showed on the previous slide. In particular, I already said we need inversion symmetry and 4-fold rotation symmetry. in order to protect the Dirac points. And so for any 2D slice of this material, which is perpendicular to the z-axis, I can ask, what is the quadrupole invariant of that slice? And that answers the question, does it have corner states or does it not have corner states? And what we found in this paper led by Ben Weider is that the planes in between the Dirac points will have a higher order TI quadrupole index. And then when you jump, so there's a bunch of planes, and then eventually you'll have a plane with the Dirac point. And then when you look at the plane above the Dirac point, that quadrupole index is now 0. And so for this intermediate set of planes, they will all have corner states. That's what these charges are meant to show, or circles are meant to show. And then therefore we're on this 3D material where two surfaces meet, there'll be a series of mid-gap modes. And so that's what we're calling higher order Fermi arcs. These modes are localized on a hinge where two surfaces meet, and they end at the projections of the Dirac points on this hinge. And so I should say that what we're thinking here is this hybrid real space momentum space picture that I talked about for Vial fermions. Here, the z direction is infinite. So we have a kz, a good quantum number in momentum space in z direction, but the x and y directions are finite. And so we're talking about surfaces which are normal to x and y. And then the hinge is the place where those two surfaces meet. And so this is some example of this hinge band structure. So again, it has one good momentum, which is the infinite direction. So that's what we're plotting. The spectrum is a function of that. And we can see that in the middle, we get some kind of insulating phase. But here, where we have these planes that have the non-trivial quadrupole index, we get these corner states. You can't see from the plot that they're corner states. All we see is that they're mid-gap states, which are between localized in the gap away from the Dirac points. Now, in this particular plot, actually, we don't have time reversal symmetry. We just have the product of inversion and time reversal together. But we can actually get more material candidates if we consider time reversal invariant systems. The only obstruction is that a lot of these time reversal invariant systems also have surface states because they have 2D planes, which are 2D TIs. And so some examples that we considered were cadmium arsenide and potassium manganese bismuth. And so what we see here, so it's a little bit tricky to interpret. This flat band is this flatness here. And the Dirac point, which is this little point, is zoomed in here. And so this is the higher order Fermi arc, this mode which is occurring inside of this very small gap on either side of the Dirac point. But you also have surface states at the projection of gamma, because in this material, as well as cadmium arsenide, that 2D plane is a 2D TI, which contributes surface states.
Hey, Jennifer, there are two questions already. Is there a similar to Vial semimetals? There are that states that Dirac points must appear in pairs. Is there a similar?
Yes. So,
okay,
right, the Dirac points, yes, the Dirac points also, actually, I think it's a little bit simpler than that, which is that since we have time reversal and inversion, we always have, if there's a Dirac point at K, there's always going to be a Dirac point at minus K. So that's one way to think of it. But yes, there's also some modification. Yeah, you can also think of some modification of the Nielsen-Ninomiya theorem, or whatever theorem you want to use to say that there's two Vial points. This also has to occur for Dirac points by continuity of, basically by continuity of the band structure. So you have two bands crossing at one place, but they have opposite eigenvalues. And since the Bruin zone is periodic, they have to cross back again to satisfy that. So these types of Dirac points always occur in pairs. Now, the quadratic Dirac points that were asked about earlier, those don't have to occur in pairs. So again, those are a little bit different.
The next one is, are the Fermi arcs degenerate, or why are they called higher order?
Right. So higher order is referring to this is meant to be an analogy to higher order TIs. Higher order TIs have gapped bulk, gap surfaces, and gapless where two surfaces meet. And that's how these Fermi arcs are. There's a gapped surface, but these Fermi arcs are where two surfaces meet. So that's what the higher order is referring to.
Mm-hmm. And so the materials you just showed, is this without a standard magnetic field?
Yes, right. There, did you say standard magnetic field? But these materials have no magnetic field.
Yeah. Okay. Yeah, thank you.
Great. Okay, good. And so now, so I guess the other thing I don't think I said explicitly, so just to say, this invariant now is directly analogous to Vial fermions. In Vial fermions, we talked about how you can take a Chern number of 2D planes and the Chern number is going to jump as you cross the Vial point. Here we're saying you can take the higher order TI or quadrupole index of a 2D plane, and that index is going to jump as you cross the Dirac point. So I think this is a very satisfying analogy. And in addition to that connection, it's also satisfying because it gives us this bulk hinge correspondence, which I would say firmly means that Dirac fermions do have a topological attribute to them. So I want to make a few more comments on the topological classification of Dirac points. So first, just to advertise my own work, although it's unpublished at the moment, working with my student Yuan Fong, what we showed is that the argument I just gave for the higher order Fermi arcs was only discussed in the context of fourfold rotation symmetry. And so we can make this better. We've extended this classification to other rotations, and we see that there can actually be multiple types of Fermi arcs that have a more complicated algebra associated with them. And so we think that this firmly answers the question of what kinds of Dirac points can have higher order Fermi arcs. But we are by no means the first people to try to classify the topology of Dirac points. So I'll just show some of these earlier references. First, by Yang and Nagaosa, what they did to classify Dirac points was look at the topological invariance of 2D planes. So you have some Dirac point along a high symmetry line, and you can ask what's the 2D TI index of the gamma plane versus the KZ equals pi plane and compare those. And that serves as some other kind of classification. You can also look at mirror Chern number. Then there's, I guess 1 year later, some other really nice paper by some overlap of authors where they do something similar to what I just discussed. They consider a Dirac point as a crossing of different types of eigenvalues, and they can assign a topological charge based on the difference in the eigenvalues that cross. And so they also give some kind of classification, which will say every time two bands with different eigenvalues cross, that contributes 1. And if you have multiple of these, therefore we have some kind of Z index. And in the C6 case, they find that there's 2 different types of crossings. That's because there's 3 different flavors of eigenvalues corresponding to the 6 roots of -1. And so there you can say, if type A and type B cross, that gives me 1 Z index. If B and C cross, that's another Z index. So they get Z cross Z. So this is another classification, topological classification of Dirac points, similar and different to our work. And then extremely recently, less than 1 year ago, there was another paper classifying the topology of Dirac points. And here, what they're really doing is establishing that Dirac points are a source of Berry curvature. It's just not the same Berry curvature we were talking about before. It's a non-abelian Berry curvature, which is over, basically you need to symmetry resolve your Fermi surface because you have degenerate bands. And once you symmetry resolve that, you get some type of Berry curvature, and the Dirac points are a source of that. So these are all different classifications of Dirac points. And we compared our work, at least to these 2 older papers, and these 3 classifications they're not in one-to-one correspondence. Something which is topological here might not be here, or vice versa, and same with here. And so when you talk about the topology of Dirac points, you need to be specific as to what you're looking for. What we're looking for is higher order Fermi arcs. And for these other classifications, for some of them, Not this one, because they're talking about 2D invariants of trim planes, but for the others, it's not clear what the physical observable will be, although they're definitely interesting and important mathematical classifications. So I think this theory of topology of Dirac points is coming together, but there's still some questions, which are, what are the physical signatures of these other topological classifications? So, okay, so I talked about Vial and Dirac points. I want to make this distinction, which I said in answer to a question earlier. Dirac points are crossings along some high symmetry line. So it's when different erups cross each other. That's what this red is one erupt, green is another. When they cross, it's protected by symmetry. There's other types of symmetry protected band crossings, which is if you look at some high symmetry point, you can just classify the erups of that point. And for certain groups, you can get higher dimensional crossings there. So Dirac points fall into this category. I mean, Vial points are separate because they don't require symmetry. And I now want to switch gears and talk for the last little bit about these types of crossings. So, this ties into the earlier lectures. The lectures I gave. So there's symmetry protected topological fermions beyond Dirac and Biofermions. That's what I'm going to talk about for the remainder of this time. How do we classify them? Well, first off, we need to recall our discussion on space groups earlier in the week. So symmetry of crystals is classified by space groups. There's 230 space groups. If you don't include time reversal symmetry, you get magnetic space groups, and there's a lot more of these. So what's the method for classifying these types of degeneracies? In each space group, at each K, you have this little group of K, which I defined on Monday or Tuesday, the set of symmetries that leave that K point invariant. This is just saying it can be invariant up to a reciprocal lattice vector. So then if you look at some particular K point, the bands at that K point are transforming as erups of that little group. So some classification then of symmetry protected degeneracies at high symmetry points is look at the dimension of the little group. What are the dimensions, not the dimension of the group, but the dimensions of the erups of that group. Those dimensions of erups will tell us about the number of bands that can be symmetry protected and cross at that high symmetry point. So oftentimes, if we're talking about a trim point, well, time reversal will just force you to have 2D erups, but there's not any higher constraint. But in the cubic groups, then you can get 4D erups, and those will be the quadratic touchings. Actually, that's one of the things which is pictured here. And what we found is that at other high symmetry points at the corners of the Brillouin zone, then you can get even higher crossings. And so just for a little bit of history, so we carried out this procedure, which was, let's look at all the space groups, all their high symmetry points, and look at the dimensions of erups of those little groups and see what types of crossings we can get. And we carried this out by looking through an old textbook. If you're very interested in learning about space groups, then I would recommend this textbook. It has a lot of detail on erups and how to construct them. So we carried that out in a very brute force way. In 2017, with this topological quantum chemistry theory that I talked about on Tuesday, all that information is now uploaded on the Bilbao crystallographic server. So if you want to know about erups of high symmetry points, I would recommend that you look at the BCS instead of looking in this book. But if you want to know about how classification of band structures and space groups is done, then this book is a difficult but great reference. So this is the results of our search. We found that besides 2- and 4-fold degeneracies, which we already knew about from Vial and Dirac fermions, that we could get 3-, 6-, and 8-fold degeneracies. And in all of these examples, considering there's 230 space groups, this is a pretty small list. These all have a very specific property, which is that these are all non-symmorphic space groups. So I'll explain a little bit why in a moment. But these combinations of screw and glide symmetries can enforce higher degeneracies. And so, right, so these are some of the main messages. 2, 4, 3, 6, 8, those are the only degeneracies that are possible in crystals if you for generic band structures, so i.e. not fine-tuned. And this is including time reversal and spin orbit coupling. If you don't have spin orbit coupling, you can actually get a couple of higher degeneracies. And these things are now called multifold fermions, and they're only available in these certain space groups, which I've enumerated here. So now I want to give a couple examples of these multifold fermions. The first example, which I think is the most interesting, one of the most interesting, is what we call a spin 1 Vial fermion. The Hamiltonian looks like this. So you can see the similarity to the Vial Hamiltonian, but instead of being Pauli matrices, these S's are spin 1 matrices. So that's why we called it a spin 1 Vial. And so again, like I said, for Vial fermions, the Hamiltonian doesn't have to look like this. It can be tilted and deformed, but this is kind of the canonical form. And in this form, we can exactly diagonalize and see that we get one flat band. This will just be flat to leading order, not completely flat, and then two other linear bands. And again, we can compute the Chern number of each band. What that means is the same thing it meant for Vial fermions. We take a Fermi surface at an energy in this band and compute the Chern number of the Fermi surface. And this top band will be +2 and the bottom band will be -2, or vice versa. So this thing is a charge 2 source of Berry curvature. It only occurs in 2 types of space groups. And since it's a 3-band crossing, it does not occur at trim points. It occurs at this P point, which is not a trim point. And so to give a little bit of intuition as to how you can get a 3-fold degeneracy, what happens is that normally with spin orbit coupling, a 2-fold rotation, if I square it, will square to -1, because basically that's a total of a 2π rotation, and fermions get a -1 under 2π rotation. Similarly, a 3-fold, if I cube it, will give me -1. But in these non-symmorphic space groups, something different can happen, because you're not just doing a rotation, you're also translating. And so those translations give you a phase e to the I kt. So at some trim points, that phase will cancel your -1 and give you a +1. And so in that sense, these crossings are, we can get an integer spin here because these things are behaving locally like bosons instead of fermions, just in the sense that a 2π rotation is giving you a plus instead of a minus. And so that changes the degeneracies that you would normally get. These are still fermionic excitations, so I wouldn't read too much into that. But locally, if you look at those degrees of freedom, it's transforming like a spin 1 object. So at this particular P point, because of this property, we can only get either 1D or these special 3D ERFs. And this is due to the non-symmorphic symmetry, which is changing these phase relations. So that's why the non-symmorphic symmetries are playing an important role. So we built some tight binding model, which is meant to realize this. It's just some fictitious thing, not based on any real material. And we see that if we look at the P point, we just get 1 or 3-fold crossing. So these are the things that we're interested in. And so then we can look at the surface spectrum. And so we get some, if we were moving kind of from these P points inwards to gamma, there's a lot of states in here. And so that's what this kind of tornado of states is. This point is the projection of the P point. And so we can very clearly see that we get 2 Fermi arcs coming out of this point. And that's because these spin 1 vials are, like I said, a charge 2 source of Berry curvature. So they'll always give us 2 Fermi arcs. It means that nearby planes have a Chern number of 2. And actually, if we take a loop in this direction and plot energy as a function of momentum around this loop, then we can clearly see that these 2 states have a chirality. They're connecting the valence and conduction bands, and there's 2 chiral states, which is necessary and sufficient to say that the 2D plane that this is outlining has a Chern number of 2. We can also look at Lando levels for this. And what we see is that because of this Chern number of 2, there's 2 chiral Lando levels. So if I take some constant slice, I'll always, up here, we have some bands which contribute negative slope and positive slope. They don't contribute to the chirality. But then we have these 2 extras, and these are the 2 chiral Lando levels. And you see that they only move in one direction. So this is similar to the Vial points, which have one chiral Lando level, which only moves in one direction. But the level spacing here is similar to the level spacing of a Dirac cone or a single Vial point. It goes like root n, that's coming from the linear bands. And in addition, because of those flat bands, that flat band at zero energy, then we also get a series of Lando levels that are kind of localized in a small window around zero energy. So this is a pretty distinct structure of Lando levels, similarities and differences from normal Vial fermions. And there's some materials, some candidate materials that we propose. And I guess the thing to highlight here is that this idealized version of a linear band crossing in a flat band is not so ideal in real materials, at least the ones that we originally found, because these bands, it's flat over only basically a zero window of the Brillouin zone. These things are immediately curving downwards. And so these materials, it's going to be possibly difficult to observe, even observe things like Fermi arcs, because there's a lot of other bands nearby. And here's some other material candidates. So since I'm running out of time, I'll just try to wrap up in the next few minutes. So the interesting thing is that these things actually have been observed in the past couple of years since we predicted them, but they're observed in a different way than we predicted. So we were looking at materials with spin orbit coupling, but actually in this cobalt silicide, which has smaller negligible spin orbit coupling, you get different degeneracies with or without spin orbit coupling. Makes sense because spin orbit coupling will, can give you a spin degeneracy or it can split spin degeneracies. And so in this material, you get these spin 1 Vial points at the gamma point. And so they see these in the bulk band structure. So that's what this paper is. But theoretically, you can also look at the surface states, and then you can see this thing is a spin 1 at gamma, and it has these 2 Fermi arcs that are coming out of there, consistent with the Chern number of 2. And this comes back to the earlier question: can you predict the shape of Fermi arcs? This would have been a very hard one to predict. They have this kind of weird serpentine structure winding around. And so the Fermi arcs in real materials can take pretty exotic shapes. You can also have a spin 3/2 Vial. These have also been predicted and observed in some materials. And again, these things will have actually even higher Chern bands. And so you get even more Fermi arcs, which are winding around the surface Brillouin zone. And there's been some really interesting work of these spin 3/2 fermions in different materials of this structure type. So this is just one example where you can see these things, and you can see these are the Fermi arcs, which are winding around, kind of similar to the theoretical prediction on the previous slide. So you might start to wonder, how long can we go on with this? We have spin 1/2, spin 1, spin 3/2, and the answer is this is the end of the story. As long as we are talking about symmetry protected degeneracies, actually 3/2 is the highest one that can exist in crystals. And so this is a picture of a Vial fermion. This is the spin 1 Vial I was talking about. And then these are the spin 3/2 that I was just mentioning. The last thing that I want to mention is a different type of multifold fermion, which is like a spin 1 Dirac. So maybe I'll just take the questions at the end. Earlier, we were talking about how we can think of a Dirac fermion as 2 copies of Vial fermions with opposite charge. This spin 1 Dirac, we can think of as 2 copies of a spin 1 Vial with opposite charge, and they're protected in the same way by inversion symmetry. So again, the combination of time reversal and inversion can kind of give you these degeneracies which have no net chirality, but with a field, you could split them and see that they actually consist of two chiral features. And so again, this can only occur in a couple of space groups. It looks exactly like the spin 1, but each of these bands is doubly degenerate. So it's actually a 6-fold crossing. And again, we have some materials where we can expect to see these, although it's going to be hard to probe them since there's other bands which are nearby in energy. And so I think, these ones, I don't think that there's been any observation of yet. And then the last one that I want to mention, I talked about 3/6. So how about I mention something about the 8-folds? You can also have 8-fold band crossings. Here in this example, all the bands are doubly degenerate. In lines, they emanate away and have 4-fold degeneracies. These so-called double Dirac fermions were also predicted at the same time, and at the same time out of Charlie Kane's group with Ben Weider. And so there, the interesting thing that they pointed out, which we also elaborated on, is that you can think of this eightfold degeneracy as some kind of parent state, which has a lot of different topological states embedded in it. And you can realize those by applying different types of perturbations. So if you apply strain in different directions, you can open a gap and you can get either a strong TI or weak TI. If you apply a magnetic field, you can split up these degenerate line nodes and you can split them up and get either a Dirac type crossing or two Vial type crossings. Actually, I think these are also Diracs. They're just in different directions, gapless and gapped. So this thing, depending on how you strain it or what perturbations you apply, can realize all different types of other topological phases. In magnetic semimetals, you more or less get the same types of physics, or at least from a theoretical perspective, the same degeneracies, but it's a lot more complicated. And especially what's more complicated is that in any magnetic material, there could be many possible spin configurations. And from the ab initio perspective, you need to compare the energies of all of these. So it's harder, but the end result is that you can also get these same types of degeneracies. And then there's some interesting thing that happens, which is that sometimes the magnetic space groups actually reduces the number of free parameters, just depending on how the magnetic symmetries commute or anti-commute with each other. And so you can get some more highly idealized cases. This is one of the best examples that we found, which is showing these threefold crossings at high symmetry points. And you can see the unit cell and the magnetic order is extremely complicated. So finally, since I talked a lot about current research over the past several years, I want to acknowledge my collaborators, which are theory, experiment, ab initio, and group theory. So there's been a lot of people contributing in this area from many different perspectives. And I think that's also which has made this field develop so quickly and in such interesting directions. And these are the main conclusions that I want to leave you with. So maybe just to summarize one sentence, Vial fermions are sources of Berry curvature. Therefore, they have this interesting bulk edge correspondence, and we consider them chiral. But some of the other types of multifold fermions and also Dirac fermions are not chiral. And so it remains in these cases to figure out what's the topological signatures of these symmetry protected fermions. Okay, I will stop here and take a couple of minutes for any remaining questions.
Yeah, thank you, Jennifer. There is actually one question, I think it's more than a comment, right? So I think you can simulate this spin-wide vial in superconducting junctions with three coupled Majoranas at two independent phases. I don't know if that's more a comment than a question.
Yeah, so I don't know about that. Our classification was based on time reversal and spin orbit coupling, and we did not include any superconductivity. So that would be a completely different type of classification since it has different types of requirements like particle hole symmetry. So that sounds really interesting. And right, I didn't mention anything about degeneracies in superconductors. So yeah, I appreciate that comment.
I think I can make a comment on that, if I may.
Yeah,
sorry.
please.
Yeah, so there's this, I think they fall in the synthetic systems type of ideas where you want to realize a band structure that resembles some solid state interesting band structure, and you can take this multi-terminal just of some junctions and control the phases independently, and then kind of get some dispersion relation. And there's definitely a way of doing vials. I mean, there's a way of people to make a way for people to make things that might not exist, like higher dimensions, for example, which is
right.
Interesting. And if I may, I actually wanted to ask you a question now that I mentioned this, because this question was perfect. So there's this synthetic platforms that it can do higher dimensions. And you said that you can do up to 8-fold, I guess, in 3D. So is it known, like the sequence, what are the fermions that can be made in different dimensions, or is this too complicated?
Yeah, so from my perspective, there's not like some pattern. Maybe I'm missing something, but I don't think that the 3, 6, 8 here is I wouldn't expect that from that information that you could deduce anything about the higher dimensions. So the same the same logic would apply. We need to consider, say, 4-dimensional space groups, look at the little groups, classify the EREPs. And my understanding is that once you look at space groups higher than 3 dimensions, there's just a lot of them. I don't know the number actually. I think it gets a lot more complicated, but the logic would still hold. But I don't even know if they're all enumerated or not. So yeah, I definitely don't know the answer to that. And if people can make systems that simulate higher dimensions, then it's worth looking into.
Thanks.
Okay, thank you. Irian Sanchez asks, since Biofermions can be considered as monopoles of Berry curvature, if any, what would be the geometrical interpretation of Fermi arcs and their chiral characterization?
So I guess, yeah, I don't know how to answer that. The only thing that I can say is what I said before, like if Fermi arcs are occurring at a fixed energy because they're part of the Fermi surface. But from my perspective, I also kind of like to think of plotting energy versus dispersion. And so then the Fermi arcs, if instead of plotting fixed energy, if you take a slice and plot E versus K, they'll have a chirality. So that's how they know about chirality. But I don't know if we can consider them to be themselves like a source or sink of anything. I guess the other interesting thing to say that I didn't mention is that you can also have like spin winding on these Fermi arcs. But yeah, I don't know if there's some nice analogy in the same way that Vial fermions are a source of Berry curvature.
Mm-hmm. An anonymous attendee is asking, in multifold fermions, we have different band crossings. How could we calculate the Chern number by hand or by pair of bands?
Yeah. Oops, sorry. But this is actually good. So, right. What you should do is look at a Fermi surface. So these are 3D systems. So the Fermi surfaces will be 2D, or I should say a fixed energy contour. And so, for example, if we look at this case, fixed energy, then I'll just be sitting in one band. And so then my fixed energy contour will be 2D, and I can compute the Chern number of that, no problem. In these other cases, which have multiple dispersing bands, then you'll have multiple fixed energy contours. So if I fix the energy, I'll have a contour in this band and a contour in this band, but those things won't cross each other. So again, I don't have any fundamental difficulty. I just have multiple Fermi surfaces that I need to consider, but each one is only for one band. And so I can firmly compute the Chern number of that band without any ambiguity.
Okay, thank you again. And actually, there are no more questions. Let me check the Slack channel. There is nothing there. I actually have a brief and very small question. You mentioned about using strain, right, to control or to tune topological phases. You mean uniaxial strain or biaxial compression and stretching at the same time,
right?
Or just stretching compression?
Yeah, so it kind of depends on what you want to do. So, right, if you use if you have a uniform strain, which is isotropic, then you will preserve all the crystal symmetry, and so then you won't break the degeneracy. So if you want to, you could change the dispersion perhaps. If you want to break the degeneracy, then you'll need to use strain, which is not isotropic.
Okay, yeah, thank you. So no further questions. So let's thank Jennifer Cano for these beautiful 3 talks of this week. And we will go for a break now, 20 minutes. So we will reconvene at 5 European time. So thank you, Jennifer, again, and hope to see you next year here personally in San Sebastian.
Thank you.
Thank you.